This video is the last in the series of videos on exponentials and logarithms B, and it's the second of two videos focusing on experimental data and linear models. So remember, I said to you in the last video that sometimes the results of an experiment can show that there's an exponential relationship between the two variables, and obviously because of the exponential relationship, the rapid rise and decrease that is, it can often be difficult to interpret the results, and we're able to use logarithms to convert these exponential graphs to linear graphs, and obviously that then makes it easier to find the relationship between the variables. So this time we're going to look at exponential equations of the form y equals a times b to the power x. So the proof for this one then, so we've got y equals a times b to the power x, and I'm going to take logs of both sides of the equation. We've got log to the base 10 of y equals log to the base 10 of a times b to the power x. Now on the right hand side, my argument is a product, which means that we can express that as a sum of separate logarithmic terms. My last term here, log to the base 10 of b to the x, the argument has a power, so I can make that a multiplier. So log to the base 10 of y is equal to log to the base 10 of a plus x times log to the base 10 of b. And I'm just going to rearrange that. So I've got log to the base 10 of y equals log to the base 10 of b times x plus log to the base 10 of a. And hopefully you can see here that we've got that linear relationship. That equation is now in the form y equals mx plus c, which we are familiar with because it's the form of a straight line equation. And we can see that y is equal to log to the base 10 of y. The gradient is log to the base 10 of b. X is just x, that's fine. And the y-intercept is log to the base 10 of a. And you can see here that from this equation here, which I've now highlighted, the variables for my axes are x, it's fine, we're used to that, and log to the base 10 of y. You can see my y-intercept here is log to the base 10 of a, and if my gradient log to the base 10 of b is positive, I might have a line that looks something like that. So if y equals a times b to the power x, then the graph of log y against x will be a straight line with gradient log b and y-intercept log a. So let's have a look at how to deal with this in an example. So this is example 2, because this follows on from the first video on experimental data and linear models. So the results from an experiment were noted as follows. You can see we've got values here for both x and y. We are told that the relationship between these data can be written in the form y equals a times b to the power x, and we're asked to state the formula for y in terms of x. Now this formula has already been stated, but you can see that we've got unknowns a and b here, so that's what we need to try and find out. So our solution then, now if we just, before we actually start trying to solve this, if we just look at what this graph looks like just now. Here's these 4 points plotted, and you can see that the graph gets quite steep quite quickly. That gradient is quite high, okay, so that's why it's easier to take our equation and take the logs of both sides, as we've previously done in the last slide, and get that into an equation which has a linear form. Okay, so we've got log to the base 10 of y equals log to the base 10 of b, which is going to be the gradient, times x plus log to the base 10 of a. Okay, we no longer need the exponential graph, okay, but what we do need to do, we've got x and y originally, the results from the experiment, but if we have a really look here, we've got x, that's fine. We've actually got log to the base 10 of y. So we need to take all of our values for y, 7.69, and find log to the base 10 of 7.69, and that is 0.89. We then need to take 12.94, log to the base 10 of 12.94, log to the base 10 of 16.12, and log to the base 10 of 23.10. And you can see here in our new table, we've recorded these new results with log to the base 10 of y, and the numbers are almost closer together, they are more similar, and that gives us that linear relationship there. Whereas here, you can see the y's got very large very quickly, and you can see that, well, I showed you the graph of the exponential relationship. So we've got this linear relationship now, and we can choose 2 points and calculate our gradient. So that's our y-ordinates over our x-ordinates, the difference in our y-ordinates, over the difference in our x-ordinates. So that's 1.11 minus 0.89 all over 2 minus 1.3. That gives us 0.22 over 0.7, which is 0.31 to 2 decimal places. Now remember, our gradient is actually log to the base 10 of b. So that means that log to the base 10 of b is equal to 0.31. Log to the base 10 of b is useful, I will use it later, but to be able to express my formula for y in terms of x, I actually need to know what b is. So b is 10 to the power 0.31, which is 2.04 to 2 decimal places. I now need to go about finding a. So I can go back to this formula here that I've got, log to the base 10 of y equals log to the base 10 of b, all times x, plus log to the base 10 of a. Now I can take one of my points and substitute that in for x and log to the base 10 of y, and I already know that log to the base 10 of b is 0.31. And I've used my point here, 1.30, 0.89. On the right hand side, I can evaluate that product to get 0.40, and subtracting that from both sides gets me log to the base 10 of a equals 0.49. Rewriting this in exponential form means that a is equal to 10 to the power 0.49, and a is 3.09 to 2 decimal places. And the question asked me to state the formula for y in terms of x. So here it's here, y equals a times b to the power x. So that's y equals 3.09 times 2.04 to the power x. And that is my final answer, stating my formula. So just now would be a good idea to pause the video before the screen goes blank, copy these notes down in your notes, and make sure that you complete the assigned exercise related to these questions.